So let's get into Chapter 7, Quantum Theory. We're going to totally change everything around and talk about the very tiny particles, electrons, nuclei, and light waves, things like that. Okay, so we know the periodic table, and mainly it was discovered from looking at the macroscopic world. What do we see? How do elements relate to each other? And so that's how the periodic table was organized. But to understand why the periodic table actually works the way it does, we need to really look down into the atom and look at the electrons and nuclei of an atom, mainly electrons. So before we do that, let's talk about light. Okay, so a wave is a continuously repeating change or oscillation. You've probably, if you've taken trigonometry, you've seen waves before. Light acts like a wave. It actually has oscillations in both the electric and magnetic fields as it travels through space. And just a note, all visible light is light, but X-rays, radio waves, ultraviolet, infrared are all light waves, in quotes, and they are all part of the electromagnetic radiation spectrum. Okay, so a wave can be characterized by its wavelength and its frequency. So let's look at the definitions. A wavelength, which is given the symbol lambda, the Greek symbol lambda, is the distance between any two of the same identical points on a wave, any two adjacent identical points on a wave. We'll see a picture in just a second. And then the frequency, which is given the symbol nu, the Greek symbol nu, is the number of wavelengths that pass a fixed point in 1 second. Okay, so here's a wave, and so you can see here there's different ways that you can measure the wavelength as long as you pick the identical point on two adjacent waves, and then the distance between them is the wavelength. And here you can see frequency. Frequency, if you look at the dotted line, if you just count how, and then 1 second goes by from the start to the dotted line, and you can count how many waves pass by during that second, that is the frequency. So you can see the top one has a frequency of 2 per second, 2 waves per second, and the bottom one has 4 waves per second. We can also use the unit hertz, which means per second. You can see that here that wavelength and frequency are inversely related. As the wavelength gets shorter, the frequency gets higher. Okay, in an inverse relationship, the product of the frequency times the wavelength equal a constant. And in this instance, the constant is the speed of the wave, which we're going to use as the speed of light. So C is the constant, 2.998 times 10 to the 8th meters per second. Okay, so lambda times nu, wavelength times frequency, equals C, the speed of light. So it's really handy because if you're given the frequency of light, then you can find the wavelength. If you know the wavelength, you can find the frequency. Okay, so let's do an example. A laser used for eye surgery has a radiation of wavelength 640 nanometers. What is the frequency of this laser? Okay, so C equals lambda nu. We know, just realize that C is in terms of meters per second, and so you have to make sure that your wavelength is in meters and that your frequency is in per second. So if we convert 640 nanometers, which is 640 times 10 to the minus 9th meters, notice it's actually technically correct to write 6.4 times 10 to the minus 7th meters, but you know, if you're just using it in the calculation, you can leave it times 10 to the minus 9th since it's easier to see. All right, so if we plug that in, then frequency equals C, the speed of light, 3 times 10 to the 8th meters per second, divided by lambda, 640 times 10 to the minus 9th meters. Meters cancel, and we get inverse seconds, 4.69 times 10 to the 14th inverse seconds, or hertz. Okay. Another example, an FM radio station broadcasts at a frequency of 103.4 megahertz. What is the wavelength of this frequency? So 1 megahertz is 10 to the 6 hertz, or per second. And so notice mega is 10 to the 6. So we need to convert 103.4 megahertz multiplied by 10 to the 6. So we get 103.4 times 10 to the 6 hertz. And then we can plug that in the equation. C, in this case, we have 4 significant figures. So C is 2.998 times 10 to the 8th meters per second, divided by 103.4 times 10 to the 6th per second. The per seconds cancel, and we get 2.899 meters. Just think about that. That's, about 3 meter sticks long, which is, a radio wave going around us. It's pretty long wave. And if you hear of long wave radio, that's exactly what it means. They're long waves. Okay, so the range of frequencies and wavelengths for the electromagnetic radiation is called the electromagnetic spectrum. And then visible light is only one small portion of it, and it goes from about 400 nanometers to about 800 nanometers. Okay, and then obviously beyond these extremes, we can't see these kind of radiation, but we can detect it with in other ways. So here is the electromagnetic spectrum, and you can see that we go from 10 to the 20 per second, which is very, very, very high frequency, very, very tiny wavelength, 10 to the minus 12th meters, or 1 picometer. Those are gamma rays. X-rays are a little bit lower frequency. Then we have our ultraviolet, which is still higher frequency and smaller wavelength than visible light. Visible light, as you can see, are around 400 to 800 nanometers. And then a little bit lower is the infrared. So infrared is, our heat energy. Oh, and I sort of, obviously, the ultraviolet is what comes from the sun, and so that's a little bit higher energy or higher frequency than visible waves. And then down at the far end, we've got microwaves, radio waves, radar waves, and then radio, TV, FM, AM. This is a nice little graph that just shows you relative frequencies and lengths of wavelengths. So for gamma rays, the wavelength is about the size of a nucleus, and then for an X-ray, the length of the ray is about, or length of the wave is about the size of an atom. In ultraviolet, it's the size of a molecule. In visible, it's about the size of a protozoan or a 1-unit cell. Infrared is almost now visible, where it's about the size of a needle point. And then microwaves, and of course microwaves and radio waves get on to the height of humans and even tall buildings or football field length. Okay, so by the early part of the 20th century, the wave theory of light seemed to be well entrenched. It was Albert Einstein who shook the boat a little bit and said, no, light has both wave and particle properties. And he said this because of the photoelectric effect that he observed. What is the photoelectric effect? Well, if you shine some light onto a piece of metal, a metal surface, and you shine the correct wavelength on it, electrons will be emitted from that metal surface and create electricity. Einstein based this idea from work from Max Planck. Okay, so this is just showing the photoelectric effect. So if you hit just the right energy, those electrons will leave the surface of the metal and be attracted to the positive wire. And in fact, the photoelectric tube, this tube was used, was the precursor to the television. Okay, so Max Planck looked at these atoms, and he said, well, they all oscillate with a definite frequency. And so it's kind of still with the wave part of light. So he proposed that an atom could have only certain energies of vibrations. For example, so E equals NH nu, where N just is as a integer, 1, 2, 3. So you could only have different energy levels. H is just a constant. It's called Planck's constant. You can see it there. And of course, nu is frequency. So that means that atoms can only have certain energies. And it turns out it's electrons that we're talking about. But atoms can only vibrate at certain energy levels, at H nu, 2H nu, 3H nu, and so forth. And so these numbers, 1, 2, 3, 4, are called quantum numbers. And so energies are said to be quantized, meaning that they can only happen in fixed amounts. So energy can either be released or absorbed only in certain amounts of energy, not any old energy willy-nilly. So in a way, it's sort of like stair steps. You can only be on certain levels. You can jump to the next level, you can jump back down, but you can't exist somewhere in between. So you can only exist at those levels. Unlike a ramp, which means you could stand anywhere along the ramp. Energy in atoms are more like a staircase. Okay, so Einstein used Planck's work and then talked more about light itself. So he's saying, okay, if the atom changed energy from 3H nu to 2H nu, that it decreased by 1H nu, it gave off that amount of energy. And so then he proposed that this energy would be emitted as a small amount, a bit of light energy. We call those bits of light energy, now we call them photons. At the time, he just called them quanta of energy, but now we know that they are photons. Okay, so again, E equals H nu. Energy is related to Planck's constant times the frequency. And he went on to use this to explain the photoelectric effect. So, of course, we know the photoelectric effect is when electrons are ejected from the surface of a metal when light shines on it. The electrons can only leave if there's the correct frequency shined on it. So violet light, which is a higher energy light, will make, if you use metal as potassium as your metal, violet light will allow the electrons to escape from potassium. However, red light, which is a little bit lower frequency light, won't have any effect on that. So you can see that in this picture. The red light, no electrons ejected. Actually, 550 nanometers is the very minimum that will allow it to happen. And then if it's a little bit higher frequency, it will also allow it to happen. That's the photoelectric effect. Okay, so Einstein's assumption that an electron is ejected when struck by a single photon implies it behaves like a particle. The energy is taken up by the electron. So when the photon hits the metal, the electron jumps up to a higher energy level. The photon ceases to exist as a particle and is absorbed as energy. And so this is the wave-particle duality of light. That light is actually a particle and light is also a wave. This equation, E equals H nu, displays that duality because E is the energy of the particle, frequency is the wave, the frequency, nu is the frequency of the wave. All right, so now we're just going to use this equation. What is the energy of a photon corresponding to radio waves of frequency 1.255 times 10 to the 6 inverse seconds? All right, well, we know H is a constant, and then we know what nu is, so we substitute that in, do the multiplication, and the energy is 8.316 times 10 to the negative 28th joules. Okay, so Niels Bohr actually took some of this information that we just learned and applied it to the hydrogen atom. because it's the simplest, obviously a hydrogen atom only has one electron, so it's going to be the simplest atom and the easiest to explain. Okay, so before we do that, let's look at the line spectrum of atoms. Okay, when we know that if white light passes through a prism, we get the different color spectrum. It's because each of the colors have a different wavelength, and so they're bent at a different angle. So white light contains all the different colors. If we take if we take white light and pass it through a slit, again, we'll get all the colors. It will give us a complete rainbow. But what if we take a particular gas, such as hydrogen, and we heat it up and allow it to get excited so that it gives off this light energy. And so it emits these photons of energy, and we send it through a prism. Notice that what we get is just a few different colors. Okay, this is called atomic line spectrum because only a few colors are observed. Here's a couple of different line spectra. The hydrogen at the top, you can see there's really 4 major lines, kind of a blue, a purpley blue, a more blue, solid blue, and then a blue-green and a red. Helium, you can see, has about 6 lines. Lithium has some major lines. Sodium really only has one big fat line right around 580 nanometers, the yellow. Calcium has a number of lines. So this is the line spectrum. So why does this come about? Well, let's talk about J.J. Balmer, who was looking, remember right now we're talking about hydrogen, looking at the spectrum of hydrogen, which are those four lines. And he made up this equation to see how the wavelength of those lines were connected to each other, or how they were related to each other. And he came up with this equation. 1 over lambda equals 1.097 times 10 to the 7th inverse meters, and then that quantity 1 over 2 squared minus 1 over n squared. And he plugged in different numbers for n, different integers, 1, 2, 3, 4, 5, etc. It turns out that if you plug in 3 for n and solve that equation for wavelength, you'll get the first line, I think the red line in that hydrogen. If you plug 4 in and solve for wavelength, you'll get the second line. If you plug 5 in, you'll get the third line. If you plug 6 in, you'll get the fourth line. And so he was able to see how those lines were connected to each other by one equation. There are the lines again. So the n equals 3 will give us this red line. N equals 4 give us that blue-green line. N equals 5 gives us the solid blue line. And n equals 6 give us the more purplish line. So having observed this, he set down some postulates to account for this. He wanted to know what made the hydrogen atom stable, and then also what made this line spectrum of the atom. Okay, so the first thing that he said, and it kind of relates to what we talked about earlier, electron can only have specific energy levels. And so instead of talking about the atom in general, now we're going to focus more down on the electron. So electron can only have specific energy levels, and we're just going to call those levels 1, 2, 3, 4, 5. So n equals 1, 2, 3, 4, 5. Those are the on and on. So here's just a picture of it. These are just the different levels. An electron can be at level n equals 1. It could be at n equals 2, 3, 4, 5. And so he derived the formula, which looks a lot like the other formula that we saw, but this one is going to be a little bit more generic. And he said the energy of each line is equal to negative RH over n squared. RH is just a constant. You can see that number there. You probably want to know that number for the test. I think I'll probably put it on the test, but you'll need that constant fairly often for these calculations. And then, of course, n can equal 1, 2, 3, etc. So energy levels are for all integers, n. The more negative the energy, the lower the level. We know that if n equals 1, that's the lowest energy level, and that as n increases, the energy increases. But as if you look at that line again, we'll look at it in just a second. They're not consistently different. The space between them is not consistent. So there's a bigger space between 1 and 2 than there is between 2 and 3, etc. If we make n equal to infinity, that means the electron has totally been removed from the atom. Okay, and then Bohr's second postulate says that electrons can transition between these energy levels. Of course, they can't exist outside of those levels, but they can transition between the levels. If the transition goes from a high level to a low level, it's decreasing in energy, and that energy is emitted. If the transition goes from a low level to a high level, that means that a photon had to be absorbed to get to that higher energy level. So here's the picture again. So you can see we have our different levels, n equals 1, 2, 3, 4, 5, 6. And what they're representing here are all the different transitions. So the very first line is a transition from n equals 2 to n equals 1. And then n equals 3 to n equals 1. So all those purple lines are transitions from those levels down to level 1. And it turns out if you calculate the wavelength of those transitions, they're all going to be in the ultraviolet region. If you do a transition from 3 to 2, you see that red line. If you go from 4 to 2, it's a green line. The 5 to 2 is the blue line, and 6 to 2 is that violet line, and they all fall in the visible spectrum. And it kind of relates back to Balmer's equation that we saw a little while ago. In fact, they're very connected. If we then if we plug in the transition from 4 to 3, 5 to 3, 6 to 3, those all happen to be in the infrared region. Okay, so again, if the electron goes from a high level to a low level, energy is emitted at a photon. E equals h nu, and we just have, it's actually delta E, so it's the final energy minus the initial energy gives us delta E. Now, if we plug this into the equation, so if the final energy, you can see on the right, is negative RH over NF squared, N being the final, F meaning the final level, and negative RH over NI squared, where I is the initial level, if we plug that into this equation, and you won't have to derive this equation. I'm just showing you that when we make those substitutions, we plug in, that negative RH over NF squared for EF, and then the other one for EI. Rearrange it, we get this equation right here, which is a really good equation to know. So delta E, the change in energy, which equals h nu, is equal to negative RH, and remember that's just a constant, times this quantity, 1 over F final squared minus 1 over N initial squared. And those N's, remember, are just integers, 1, 2, 3, 4. So if we're going from the third level to the first level, then the final would be 1 and the initial would be 3. If we're going from the 6th level to the 2nd level, then the final would be 2 and the initial would be 6. If we're going the opposite direction, from 2 up to 6, we'll be absorbing energy, and final would be 6 and initial would be 2. So we're going to do a few examples in just a second. Okay, so Bohr's theory explains the emission of light, but also the absorption of light. So like I said, if an electron falls from 3 down to 2, that energy emitted is at wavelength 685 nanometers. And since the final level is lower than the initial level, then delta E is negative and energy has been released. However, if we put 685 nanometers, if we put light of 685 nanometers and shown it, it could be absorbed, and then the electron could absorb it, go from the 2nd level up to the 3rd level. Delta E is positive, but note that it's the same exact amount. So the distance between those levels is the same whether you're going up or coming down. All right, so let's do an example. Calculate the energy of a photon of light emitted from a hydrogen atom when an electron falls from the 5th level down to the 2nd level. So we have our equation. It starts at 5, so that's our final, that's our n initial, and 2 is our n final. So if we plug those numbers in, and I wouldn't bother doing a whole lot of bad calculations. Your book goes through, if you read the example in the book, they kind of try to find fractions and least common multiples, and I think that's crazy because you have a calculator. So just take 1 over 2 squared, which 1 over 4 is 0.25, and then subtract 1 over 25, and you'll get that 0.21. And then take that and multiply it by negative RH, which is the constant, and we'll get negative 4.58 times 10 to the minus 19th joules. So that's how much energy is released when an electron goes from n equals 5 down to n equals 2. It's negative because we're going from a higher level to a lower level. If the energy were to be absorbed, it would be a positive number. Here's what I said. Just solve it with a calculator. I think your book makes it more difficult than it has to be. All right, now that we know the energy of the photon being emitted, we can calculate the frequency and wavelength of that photon. Since we know delta E equals h nu, and since we know we know E, we can find nu. Nu equals delta E over h. H is just a constant. So you can see here that the frequency is 6.91 times 10 to the 14th inverse seconds, or hertz. And if we want to, we can also calculate the wavelength of that frequency. So wavelength is just c over frequency, 3 times 10 to the 8th divided by 6.91 times 10 to the 14th. The per seconds cancel, and we get 434 nanometers. This wavelength is in the blue-violet spectrum, and so we saw it on that hydrogen spectrum. It is the I think it's the fourth light, or the third blue on the spectrum, or the second one from the left. Okay,